Hello everyone. In the previous video we studied about the rectifier. What is a rectifier? What are all the kinds of rectifiers? And we studied the halfway rectifier. Knowing the concepts of halfway rectifier, the disadvantage of halfway rectifier is first one, its efficiency is equal to only 40.5% and it is going to have a ripple factor of 1.21%. which led to the full wave rectifiers. Coming into the full wave rectifier, we have two kinds. One is a center tap rectifier, or we also call it as a two diode rectifiers. And the second one is the bridge rectifiers. So let us study the center tap rectifier for this class. In the center tap rectifier, we are going to have primary winding of a transformer where we are going to give the AC input supply. At the secondary winding of the transformer, I can have the same voltage, but the kind of transformer we are using here is a center tap transformer. What is the center tap? What is the difference is, in the center tap transformer, we are going to connect our load resistance exactly at the center of the winding of the secondary winding of the transformers. That is RL, the load resistance. In the center tap rectifier or the full wave rectifier, we are going to replace in the half wave, that is by two diodes. In the half wave rectifier, we were using only one diode, but when we come for the full wave rectifier, we use two diodes. That is, center tap rectifier uses two diodes, that is diode D1 and D2. Coming to the input, the AC signal which is getting rectified, we know the rectifier is the one which is going to rectify the AC input into the DC output. During the positive half cycle of the input, the diode D1, that is the polarities across the center tap rectifier, is going to be positive, this is negative, this is positive and negative. Now, during the positive half cycle of the input, the diode D1 is going to be forward biased. As a result, it acts as a closed switch, and during the same positive half cycle, the diode D2 is going to get a reverse bias and it is going to act as a open switch. So as a result, for the first positive half cycle, diode D1 is on and my diode D2 is off. Similarly, for the next negative half cycle, the polarities at the diode at the secondary winding of the transformer is going to be negative, positive, positive, positive. Now when we look into the polarities, I can say my diode D1 is going to be reverse bias and my diode D2 is going to be forward bias. So for the negative half cycle of the input, my diode D1 is not conducting, but my diode D2 is conducting. That is, D2 is on. So as a result, can I not say we can expect at both the cycles of input, I can expect the conversion from AC to DC. That is, for the positive half cycle also, the diode is conducting, diode D1, and for the negative half cycle, my diode D2 is conducting. This is how the working principle of full wave rectifier is that is explained by using the waveforms. Now let us look into the average or DC current. When we come for the average or DC current, it states that my IDC is given by the formula is equal to area under one cycle of the output current divided by time period of the output current, right? So IDC is equal to time period. We know it is nothing but my IDC is equal to integral of 0 to 2 pi I naught d omega t, where my I naught is nothing but Im sin omega t by 2 pi, that is this is equal to time period is 2 pi. So this is equal to 0 to 2 pi. Now we know my half full wave rectifier is going to provide me output for the entire one full cycle of the input, right? So as a result, instead of splitting, instead of if I split the limit from 0 to pi and pi to 2 pi, it is nothing but I can write this as 2 into 0 to pi Im sin omega t divided by 2 pi into d omega t. So that is, once we substitute this and we take the limit, and we can say our IDC is nothing but 2 Im by pi. Similarly, let us calculate VDC, which is nothing but IDC into RL. Substitute for IDC, it is 2 Im by pi. Im is nothing but Vm by RL. RL gets cancelled and it is VDC is equal to Vm by 2 Vm by pi, right? Well, let us calculate the RMS value. RMS value or the RMS load current, which is given by RMS value is equal to square root of area under 1 square of the area under one cycle of the output current divided by time period of the output current. So IRMS would be equal to square root of 1 by pi integral from 0 to 0 to pi I squared L into d omega t. We already know why it is 1 by pi, because it is nothing but the same, that is we are going to expect the output at both the half cycles. So as a result it is 2 into 1 by pi, so which is going to be 2 gets cancelled and directly we are substituting 1 by pi. Okay, so substitute for sine squared omega t, that is 1 minus cos squared omega t by 2. Substitute. Once we substitute it and apply the limits and integrate and apply the limits, we are going to get the VRMS as equal to Vm by root 2 and IRMS as equal to Im by root 2. Now after knowing the RMS current and voltage, let us calculate the efficiency of the center tap full wave rectifier. We know the efficiency provided by the half wave rectifier is only 40.5%, due to which we are into the full wave rectifier, which is a center tap full wave rectifier. Here we are going to replace the diode by two diodes, D1 and D2. Now let us look into the efficiency, which is given by eta, or which is denoted by eta. We know it is defined as ratio of DC power delivered to the load, that is PDC divided by PAC. DC power delivered to the load to the AC power to the second supplied for the secondary of the transformer. So eta is equal to PDC by PEC. Now let us individually find out what is PDC and what is PAC. PDC is equal to I square DC into RL, where we know IDC for a full wave rectifier is 2Im by pi. Substitute it, put a squared and get the expression for PAC. Similarly, let us calculate PDC. Similarly, let us calculate for PAC, which is nothing but my RMS squared, IRMS squared into RF plus RL. Now substitute. Once we substitute it, our efficiency would be equal to 81.2%. So what is the inference? What is the inference of once we get the efficiency? By looking into the efficiency, I can say out of 100% of the AC input, I can have 81% as my DC output, 81.2% as my DC output. So as a result, I can see there is an increase in the efficiency whenever we use a full wave rectifier. Now, after knowing the efficiency part, let us find out the ripple factor. Ripple factor is nothing but, which is given by gamma is equal to ratio of RMS value of the AC component of voltage or current to the DC component of component of voltage or current, which is given by gamma is equal to square root of IRMS squared minus ID squared DC by 1 whole square. Substitute, we get for the full wave rectifier, the gamma is equal to 0.483, which indicates that the center tapped transformer full wave rectifier, the AC component across the load RL is equal to 0.483 times that of the DC component. Now, after knowing the ripple factor, let us go for regulation. Regulation is nothing but it is the measurement of how well the rectifier is going to maintain a constant voltage in the presence of load and no load conditions. Load and no load conditions. So the voltage regulation is given by VNL, that is no load voltage with full load divided by voltage with full load into 100%. We know with no load it is equal to V2 into Vm by pi. With full load it is IDC into RL divided by IDC into RL into 100%. So the voltage regulation is given by RF by RL into 100%. Knowing the concepts of full wave rectifier, I can say the advantage of full wave rectifier is the efficiency is increased to double of it. That is, I can say by using two diodes, we can increase the efficiency. We were expecting the efficiency to be doubled. When we compare with a half wave rectifier, the efficiency is 40.8% in the half wave rectifier and it is 81.2% in full wave rectifiers. Thank you. Thank you for watching the video.